So this time I'll be talking about neural semantic parsing. This time is significantly more applications oriented and less algorithms oriented than the previous time. So I'm going to be talking about a lot of things you can do with a lot of the methods that we have, but we have there is a little bit of like the special stuff that you need to do for semantic parsing mixed in there. But I'm happy to take lots of questions this time because I also don't have a huge number of slides. The reading material was just it was recommended but not required, and part of the reason why was because there was lots of it. But if you're interested in semantics, I think it was explained quite well in a way that you don't see a whole lot of in papers. So it's very like I don't know. The material seems a little bit old school in some ways, but knowing the material well can help you come up with good ideas for your new neural methods. So what we talked about the past two times was tree structures of syntax, like dependencies or phrase structure. And these, basically show us the structure of the sentence, but sometimes we'll also want to handle semantics. In semantics, basically, we would like to know what the sentence really means. But what does meaning mean? Like, what is the meaning of meaning is a very difficult thing to define. And if the people who did take a look at the reading material probably realize that it's very complicated and it's not easy to come up with a good semantic representation. So I think a lot of semantic parsing research or a lot of research on handling semantics nowadays kind of takes a very direct approach that grounds semantics in the particular task that you would like to be doing. So for example, a machine could answer questions. If you ask a question, is it able to answer this by accessing some database or something like that? Or follow commands. So you tell your Roomba to vacuum this half of the room, and it vacuums only this half of the room instead of vacuuming like this room, the entirety of this room and your kitchen and your foyer or whatever. Unfortunately, Roomba cannot do this yet, I don't think, but if it could, that'd be great. And then there's lots of other things that you could consider asking your computer to do. So representations of meanings, there's lots of different ones. There's special purpose representations that are designed for a specific task. There's also general purpose representations, and these general purpose representations are basically designed to allow you to do anything. And that was mainly what the reading materials were talking about. They were talking about, judging whether two sentences mean the same thing. And then you can take these general purpose representations and convert them in some way to the thing that you want to do or operationalize. And then there's also kind of shallow representations that aren't aiming to get the entire meaning of the sentence, but to get particular parts of the sentence that are that would still be useful for some particular things. So first I'll talk about special purpose meaning representations, and there's lots of examples of these. Are there any questions so far or comments? Okay. So there are some examples. So one is would be a database query language for sentence understanding. So I'm sure if you've used Google, particularly if you've used Google in English nowadays, you see that it can answer a lot of your questions. So And it can answer them in a number of different ways. Sometimes it answers your structured queries with a specific answer. So if you say, what is the population of Pittsburgh? It will tell you 350,000 or whatever it is. It can also answer lots of questions that are kind of free form with free form answers based on text. So my favorite question that I asked Google recently is, what is the difference between cured and uncured bacon? If you've gone to the supermarket, you've probably seen cured bacon and uncured bacon. Does anyone know what the difference is? No. So cured bacon apparently uses nitrates, and uncured bacon doesn't use nitrates or something like that. But anyway, if you ask Google that, it can actually answer that for you. Mainly these semantic parsing things are useful for kind of the general purpose. The database structured queries that give you an answer like a number or a date or something like that, as opposed to the freeform queries. You can also think of a robot command and control language, like telling your Roomba to do something. Also, another thing that I'm very excited about nowadays that people have probably heard me talk about is generating source code in a language such as Python. And this can also be viewed as a type of semantic parsing, basically. And I'll talk about each of these in turn. So there's a bunch of query tasks. One very classic one is called geoquery. And this is parsing to Prolog queries over a small database. And this database basically is about US geography. So it's about cities in the US or whatever. So we have an example like this. So what is the population of Iowa? And then our answer is, actually this is a slightly more, I pulled this from a paper, but basically you have the population, then you have the state ID, and it's kind of a first order logic expression like this. There's also, so actually with regards to the first geoquery one, this was made by Zell and Mooney in 1996, and Ray Mooney, the guy who created this a couple years ago, basically said, why is everybody still working on geoquery? You should stop working on this already and do more interesting things. So this is kind of like the top one is kind of like the old one that people have done a lot of work on. But more recently, there's a lot of work on parsing to things like freebase and answering questions over a wide general domain thing. And that will look something like this. What are the neighborhoods in New York City? How many countries use the rupee? And so New York City will need to be mapped to a particular entity called New York out of all the millions of entities in freebase. And how many countries use the rupee would be something like this. So you kind of have these two axes. The geoquery one is it has these big trees and complicated structures and stuff like this. So the queries are very compositional. So you need to combine the meaning of multiple phrases. And then you have the domain, the broadness of the domain. And geoquery's up here. And a lot of the kind of like freebase question answering stuff is down here. And both of these kind of tend to work somewhat well. Like Google can answer your simple queries about entities and stuff. In geoquery, it's a very limited domain, and you can kind of capture the compositionality. And right now, I think people in semantic parsing are largely working to move over to these more, like expand the domain for the highly compositional stuff, or make the open domain stuff more compositional and more complicated queries. There's also a bunch of other things like web questions and wiki tables, etc. So if you're interested in this kind of semantic parsing or question answering stuff, these are some things that you can look up. Am I missing any major ones here? I think these are some of the major ones. There's also a lot of command and control tasks that you can do. So one kind of old school one also done by Ray Mooney is RoboCup. So this is one where you give natural language instructions to your robot soccer player that says go take the ball from or player number 5, go defend our right wing, or go take the ball from player number 3, or something like that. And these commands get translated into this language that the robot can then use to interpret. So here's one. If our player 4 has the ball, then our player 6 should stay in the left side of our half. So it also has conditionals, etc. There's also if this, then that. This is a kind of much more modern version. It's also more open domain. And what it looks like is call me if the Cubs score. So if the Cubs made a thing, it's from your ESPN app. If it's new in-game update Chicago Cubs, then action phone call my phone, or something like this. This is a diehard Cubs fan, I guess, because I don't want a phone call every time the Cubs are scoring. But hey, and this is actually kind of interesting. The way they gathered it was from this website that basically has a large collection of these. So there's quite a few of them, like tens of thousands to hundreds of thousands. And then there are also other code generation tasks. So this is a kind of interesting task. You basically have a card from a card game, and you can take the various attributes of the card, and then you need to go and generate a Python class that implements this card. And this is called the Hearthstone task. This is a data set that we made of Django commands. So an example command is convert call frequency into an integer and substitute it for self.call frequency. And it converts this into a Python command for you. And there's other things like this. So all of these, what you probably noticed as I was going through all of these is basically they're taking in some sort of natural language and creating some sort of kind of structured representation that looks like a tree, or in the case of GeoQuery, it's a tree, but it also has variables in the tree, like this. So, so those were the tasks. So if we want to create a neural model to do this, our first attempt at creating a neural model to do anything nowadays is training a sequence-to-sequence model with attention. So what we can do is basically take our regular sequence-to-sequence model with attention and then linearize the representation. So for example, if it's Python, you just tokenize it. And treat it as one long string that looks like with all the tokens and new lines, etc. You could also take the one on the top and just treat it as a token string and generate it. So does this work? The answer is no, it doesn't really work, because often in these semantic parsing data sets, we don't have enough data to learn this properly. If we have a really big data set, then it does work to some extent, but particularly for things like, this is actually GeoQuery, this is far too small for a sequence-to-sequence model to learn as is. So even in the first attempt, to do this, they were a little bit more creative than just training a sequence-to-sequence model. What they did was they took their original examples. They basically trained a traditional grammar-based model to that can map between things. So an example is what are the major cities in if they get what are the major cities in Utah and what states border Maine, they extract rules that basically map these into the logical forms or the code. And then once they have this, they can generate things from this grammar. So they just generate a whole bunch of extra data, and then they train their sequence-to-sequence model on all this generated data. And once you train the model on much more synthetic data, then that ends up giving you relatively reasonable results. But this is a little bit annoying because you have to train a regular, you need to train the synchronous CFG, and if you can train the synchronous CFG, you might as well use the synchronous CFG for parsing in the first place, or for semantic parsing in the first place. So there are more sophisticated and more clean end-to-end models nowadays. I think this general idea of generating synthetic data is a pretty good one, though, if you can come up with ways to do it for your particular task. Like there was also one for machine translation where they just swapped in other words. So they found words that matched in a lexicon, and then they swapped in other words there, and that improved the robustness of their model as well. So here's a second and slightly more principled attempt at creating a model to do semantic parsing. Actually, this paper and the other paper both appeared in the same conference, interestingly, with different approaches. But this approach was not about generating synthetic data. This was about using the tree structure of the semantic representation to basically condition things in a better way. And the way they do it is basically, if we have a tree that's lambda, let's see, lambda $0 and then it has kind of a child underneath it, and that child is and something something, then it first generates that top level of the hierarchy, then it moves down to the next level and generates everything in the next level, then it moves down to the next level in the hierarchy, etc. So basically, it generates from top down, and it passes the information from the top part down to when it generates the next candidates. And this is good because it can kind of it can pass information from the top down and generate like one basically hierarchy at a time. One kind of disadvantage of this model is that it doesn't consider what it generated down here when it's generating the stuff up here. But yeah, as I said, this is a better attempt. Any questions about this? Okay. So this is the next thing, this is not limited to neural models by any means, but it's something that if you're working in semantic parsing or thinking of working in semantic parsing, you should definitely know as a trick or as a very important piece of technology that people like to use here, which is learning from weak feedback. So one of the reasons why semantic parsing is hard is because we don't have enough annotated semantic parsing data. So we need to do, we basically need to do tricky things like generate more data or something like that. But in some cases, we can't even get any annotated data, or it would be extremely costly to get a significant amount of it. So what we can do instead is treat basically the logical forms, the structured representations that we want to use as a latent variable, and guess what that variable is, and and then when we get the answer correct, we give a boost to that particular logical form. So an example is, what is the largest state that borders Texas? And then this Z here would be our latent logical form. And this can be framed as a reinforcement learning problem. So I'm going to be talking about reinforcement learning next time. No, maybe the time after next. So I won't talk about it in detail here. But basically, the really simple summary is that every time you randomly generate one of these Z's, and if that Z is executed against a database and then you get the correct answer, you improve its score. If that Z is executed against a database and you get an incorrect answer, you decrease its score. So, and I'll talk about the math of that in 2 classes in more detail. So one of the problems with this that has been pointed out very recently in neural models is that you can get spurious logical forms. So an example of this is I want to tell my robot to bring me a Coke or something like that. And for some reason our robot is not trained very well. So I say bring me a Coke, and it thinks, okay, I need to bring the thing that's sitting on the table over here. So it interprets it to say, bring me the thing that's on the table over here. And it brings it over here to me, and it happened to get it right. And I say, good robot, good job, and then it gets its reward. But then next time I say, bring me a Coke, and this pencil is on the table over here. It goes over here, grabs a pencil, and brings it to me, and it makes a mistake. So this is a pretty big problem if you have lots of things that could accidentally give you the correct answer. So if you think about a robot type task like that, then you could think that there's many ways that it could interpret it incorrectly, but still get it correctly, still do the correct thing. And there's a paper about how to handle this by encouraging exploration and some other tricks. So another kind of topic in semantic parsing is how to scale up. So I had the thing on the whiteboard over here, which is where if we want to scale into the open domain, we're going to have to interface with a knowledge base in some particular way. And there's a couple of different ways that we can do this. I'm actually not super familiar with the literature on this topic. So if somebody else in the room knows some other relevant work that I could point out, please chime in. But one example of this in the neural domain that I found was one that basically it learns in embedding. It learns an embedding for pieces of the knowledge base, like what is the path between particular answers, or what is the what is the value, what is the answer type, what is the context of the things around the answer. And they embed them all together, and then they kind of do a Siamese network type thing. Not Siamese network, but a retrieval type thing where they match what is said in the sentence to the answer path, what is said in the sentence to the answer context, what is said in the sentence to the answer type. This was one example. I say more on knowledge bases in a month or so. I will be covering this in more detail, but I felt I will be covering this in more detail, and I will be doing a survey so I can cover this in more detail with more accuracy before then. But are there any interesting ones that I should be mentioning here? Any? Anybody work in this space? No. Okay, well, I'll defer it to about a month or so when I'll have a more complete coverage of this. Okay, so another thing I talked about was code generation, and this is something that's becoming more interesting. I feel this is very, very interesting because it's basically kind of a broader. It's like open domain semantic parsing for knowledge bases, but instead of open domain semantic parsing for knowledge bases, it's like open domain semantic parsing for command and control problems. So I think this is pretty cool. One of the things in source code is that there's a significant amount of basically copying things word for word. So for example, in code, you might say a variable name. You might say a variable name and you want it to be copied as is into code, etc. So this is a rather clever model that combines together character-based generation and copying of things. So this is a rather complicated, it's a rather clever model with a rather complicated figure. That's very good if you take a long time to look at it. But basically, to summarize, this method has the ability to generate things character by character. It can also copy names or copy other parts of this card, like the attack part, the help part, etc. And it can marginalize over the various ways that it could be generating things. So I think kind of the interesting thing about this paper is it doesn't need to decide which way it generated something. It can kind of simultaneously generate from all of them at training time, which makes things a bit easier. So this one, the other thing about code generation is that we tend to have very, very big programs compared to semantic parses, standard semantic parsing. So standard semantic parsing has these trees that are usually pretty little. They have maybe 4 or 5 internal nodes or something like that. But if you start to get a program like the one for the cards, we have these big classes that we need to generate all at one time. So there are ways to handle syntax. The code also has syntax, for example, in the form of abstract syntax trees, which so this is one of my papers with Pengcheng. But basically, the idea is if you take Python or any programming language, you can take a parser and parse it into a tree structure, and then based on this tree structure, you can generate. And the model here is very similar to the sequence to tree model, but we do things a little bit more. Basically, you can remember everything that you've generated so far, which was not the case for the tree to sequence model. And this syntax is very, very important for code generation. It's more important for code generation than it is for standard semantic parsing tasks. So this is pretty useful in this context. So that was kind of a brief overview of like special purpose meaning representation parsing. Are there any questions or discussions or things like that?
Can you go back to the tree-based parsing?
This one or the one before? Okay, sure.
So I'm really confused. What's the output?
Oh, the output is. That's a good question. So the output would basically be like, we have lambda $0 E then we have a node, I guess. And then this is and so this n is like it's like an internal node. So yeah, I probably should have shown the tree here too. But basically, that n is a internal node, and then all the text that you see down there is the stuff that's actually generated.
So actually the output is like a tree structure.
The output is a tree structure, yeah. So in semantic parsing, generally the output is a tree structure. Or a graph structure, which I'm going to talk about more next. Okay. So, so for general purpose meaning representation, there's a few desiderata, a few good things about meaning representation that we would want to have in any general purpose representation. That was also outlined in the reading material. But one is verifiability, so ability to ground it with a knowledge base, etc. This is good if you want to do question answering or whatever. Unambiguity, one representation should have one meaning. Canonical form, one meaning should have one representation. Inferenceability, you should be able to draw conclusions from this representation. And expressiveness, you should be able to handle a wide variety of subject matter with this. So there's no meaning representation that does all of these well. There are meaning representations that try very hard to do this, but in reality, satisfying all of these at once is quite a difficult task, especially the last one. But anyway, one kind of representation that it's quite common to use is first order logic. So I think most people know something about first order logic, but just in case you haven't heard about it in a while. You have logical symbols, connectives, variables, constants, etc. So, for example, there exists a restaurant X. X serves Mexican food, and the location of X is close to the location of Ixy. So you can see that this corresponds to there is a restaurant that serves Mexican food near Ixy. And all vegetarian restaurants serve vegetarian food. All vegetarian restaurants X implies serves X vegetarian food. And also, importantly, lambda calculus allows you to express functions. And this lambda calculus here is very important because you can kind of define basically many verbs or many predicates will take arguments, and based on the arguments that the predicate takes, it can swap in the things, swap in the arguments into this meaning representation. So because of this, first order logic is used pretty widely. There's of course better representations or more expressive representations, but this is kind of the go-to one, I guess. There's also a ton of other meaning representations. One that people have used quite widely is abstract meaning representation. It came out pretty recently, but it's designed to be simpler and easier for humans to read. And it's in a graph format with arguments that mean the same thing as linked together. So this looks like this. So if we have our first order logic on the top, we have instance want, instance G, Geo1, instance B, boy, arg0 WB, arg0 WG, arg0 GB. So does anyone understand this? No. If you look at the AMR format, you can see want. The argument 0 of want is boy. The argument 1 of want is go. And the argument 0 of go is boy. So that makes it a little bit more clear, right? You can kind of see that there's a boy that wants something, and that what he wants is going. So the boy wants to go. And this can also be expressed as a graph that looks like this. One of the other good things about this is a relatively large annotated tree bank is available, or they call it a SEM bank. It's not a tree bank because it's graphs, but they call it a SEM bank. So if you want supervised training data for this, you can also get it. There's lots and lots of other formalisms. A couple of them that I've seen in papers recently are minimal recursion semantics. So this is basically a variety of first-order logic. The idea behind it is that it strives to be as flat as possible to preserve ambiguity as much as you can without trying very hard to resolve it. Another one is universal conceptual cognitive annotation. The idea behind this is that it wants to be very close to the original sentence. So like try to use the words in the original sentence as much as possible while still giving a very minimum of like the relationship between all of these. And P, for example, is the predicate. A are actors in some way. And then D is a modifier and various things like that. Any questions about this? So the first thing to note is that syntax and semantics have a very strong correlation between them. And we generally have much more data that's annotated with syntax. We have the Penn tree bank that is which is annotated with lots and lots of syntax trees. We have other tree banks, etc. And because there's a very strong connection between syntax and semantics, given syntax, we can get semantics much, much more cheaply. Maybe almost automatically, not entirely automatically, but we can get a lot of the stuff that we want. So there was an example of rules that basically take CFG derivations and convert them into first-order logic in the reading materials. These were manually created rules, so they're not perfect, of course. They can't resolve some of the ambiguity necessary, but this is one example. You can also convert dependencies to first-order logic. There's quite a bit of work on this. This is a very recent one. And then there's also other methods. There's some unsupervised methods that take in dependency trees and try to convert them into logic rules. And then one other very, very popular method is combinatory categorical grammar, CCG. In converting this to first-order logic. And this has a few desirable properties that have made it very popular with people in semantic parsing, and I will explain about them next. So CCG, it's basically a simple syntactic formalism, but it has very strong connections to logical form. And syntactic tags are combinations of elementary expressions. So this is an example of what a CCG derivation looks like. So interestingly, it doesn't have any verbs. You can see here, there's no V tag, unlike the Penn tree bank. And the reason why is because all verbs are expressed in this kind of strange notation where you have S's, NPs, and lots of slashes. And what these basically mean is S backslash NP in brackets with what this basically means here is we first reduce the thing on the right side. So the forward slash means first we take this NP and we combine this thing with an NP, and that gives us the remaining thing, S backslash NP. And then we take the NP on the left side and combine that together to get an S. So you can see that's exactly what happens. Borders in Idaho get combined together to the S backslash NP, and then borders Idaho gets combined with the Utah, and you end up getting borders Utah, Idaho. And the reason why CCG is quite popular in semantic parsing, well, okay, so there are strong syntactic constraints on what tags can be combined, and much weaker constraints than CFG on what tags can be assigned to a particular word. Sorry, I thought I had an extra bullet point here, but what I wanted to say was basically it's once you have these syntactic tags, there's often a very, very strong correlation with these lambda calculus expressions. So the way you combine things together into the semantic form very strongly follows the syntax according to this formalism. So this is why people in semantic parsing tend to like this over something like CFG, which is a little bit more vague in this regard. What you should know about CCG is it has very, very strong syntactic constraints on which tags can be combined, but much weaker constraints on what tags can be assigned to a particular word. So a verb can potentially have many, many different types of tags assigned to it. For example, if it's a verb that could be I'm blanking on that name. If it's a transitive verb or a bitransitive verb, it could take a subject and an object, or it could take a subject and two objects. So it could have two different tags there. In reality, you have actually many, many more tags if you add a preposition or a prepositional phrase or something like that. So based on those two things, this introduces kind of two new methods that people like to use for these tasks. One is called super tagging. So super tagging, it's a cool name for something that's really simple. It's just tagging with a really big tag set. But the CCG symbols, there can be hundreds of them. But basically, as I said before, we have very strong syntactic constraints once we know our tags. So if we can generate those tags very, very accurately, we can basically reduce our syntactic parse candidate to 1 if we can predict the tags 100% accurately. So this is very, very effective at basically helping CCG parsing become more effective, or more accurate. So in terms of methods to solve this, standard LSTM taggers with a few tricks perform very well and improve parsing. One of the things they do is they basically model the compositionality of the tags. So we have 1,000 different tags. And because we have 1,000 different tags, we don't want to model each one of them separately because we won't be able to get the long tail of tags well. So they actually take into account the fact that this tag is basically a tree, of tags, and learn the representation for the tag appropriately for that. And they also use a few of the tricks, like scheduled sampling, which I talked about before, to prevent error propagation. But overall, it's a pretty simple model, and it gets very good results here. Are there any questions about this stuff? No? Okay. Yeah.
So once we get this representation in ML or CCG format, how can we make use of this representation to turn that into an application example for question answer system?
Uh-huh.
for an example for this application?
So that's a very, very good question. First order logic expressions are relatively simple to kind of deterministically turn into queries over knowledge graphs, etc. So, for example, borders Utah, Idaho, you could look up, what states border Texas? So you get something like this. You get something like this, and you can basically convert it into select state where a state borders Texas, or select state X where X borders Texas. And if you query a knowledge graph, they actually have a I think some people know this, but there's a query language called SparkQL that basically takes queries that look almost exactly like this. The one thing that you do actually need to be careful about is this is just using English words, right? So it's not entirely simple to go from the word border to the symbol corresponding to borders in the knowledge graph or in the SparkQL language. So you do kind of need to ground. You need to ground the word and the knowledge base together when you're creating the rules for the CCG thing. And there's learning that lexicon that basically grounds those two things together is probably the hardest part of CCG-based question answering. There's a lot of work on that, though, if you're interested, and you can look up the details. Anything else? Okay. So parsing to graph structures. So CCG is a kind of like a syntax-driven semantic parsing method. There's also methods for parsing directly to the graph structures that we want to generate. So most of the semantic representations can be represented as some sort of directed acyclic graph. So you saw the example of AMR. So AMR is basically a graph where a single node represents an entity, and they might be connected together with argument links. So a very common way to do this is to take a regular transition-based parser, where that transition-based parser normally could only generate trees, and then you modify its transition system so it's able to also generate graphs. A couple examples of this are basically creating an AMR parser where when you do write arc, it doesn't reduce. It doesn't delete the node, or sorry, doesn't delete the word from the top of the stack. And by doing this, you can basically create links to the same word over and over and over again. Another example is for UCCA adding some special transitions, and I'll give an example of this later. Another way to do this is the kind of giving up way, where you say, I really want to run my sequence-to-sequence model on a parsing task. So you basically do some sort of linearization and insert pseudo tokens for where you're re-entering into the graph. So this is another way to do so as well. So here's an example for the UCCA graph. So the UCCA graph has these internal nodes that are all linked to words. And it has kind of the normal transition system where you can do shift and reduce, for example. So shift takes one word off the buffer and moves it to the stack. Reduce, in this case, it's a little bit different from the reduce this time. This time it just removes the thing from the top of the stack, essentially. So it says, I'm done with this word. I don't need to do anything more with this word. Another thing you can do is node X. So node X basically adds a node of a particular type. And then it also creates a link, an edge from the thing on the top of the buffer to the stack. So, or to the node, I'm sorry. Or sorry, yeah, it adds the node to the top of the buffer, and then it creates a link between that and the thing on the top of the stack. So for example, if you look at the first thing here, you would first shift after and put it onto the top of the stack. Then you would create a node, do the node L action, which would then put a node on the top of the buffer with a link to after. And then it has left edge and right edge that allows you to create kind of the solid edges here. And then it also has these left remote, right remote things. So these remote edges are basically the dashed line here. So John moved to Paris is kind of the main predicate involving John. But also John graduated, right? So you can see that John and graduation are also linked as an action. So I won't go through the entire system. It also has a swap action. Let's see. So maybe you can really quickly show. So I think the difficult thing is the oracle. How to create an oracle that basically tells you what the correct action is, and I think Dan has an example of that here.
So the UCCA paper implemented their paper in Dynet in Python, and it is online. So you can go look at that if you're interested. The codes. You can tell this isn't my code because it is really clear and nicely written code. So essentially what you're doing is when you start, you define your set of actions. You have your node, remote node, implicit, then right edge, right remote, left edge, left remote. And this is what Graham was just talking about with your set of actions. Then the real sort of part where things get done in the oracle is here in generate actions. And
Can you make the window a bit wider?
yeah, is this good for everyone? Cool. So this should be I found this to be fairly self-descriptive. So when you start, you basically check if there's nothing in the buffer and the stack, and there's no edges remaining, and there's no labels remaining, you finish. If there's a stack, and the top of the stack does not need a label, you can reduce and pop that off the stack. Where was I? Then if it has a stack and there are edges remaining on incoming and outgoing, you can create these incoming and outgoing sets, but if they do not exist and you do not need a label reduce, and none of the outgoings are terminals, you can add this label. If there is incoming, that means you potentially need a new node. So if the edge's parent is one of the remaining nodes, and it's not implicit and it's not remote, you can add this edge, and then it's sort of similar for the rest of it. But I think this code is very clear on what's exactly going on. I don't know if I should walk through the whole thing.
Yeah, I don't think so. But I think this code is a little bit complicated. It's a little bit more complicated than the stuff that we saw for the other shift-reduce parser. But on the other hand, this is the most complicated part of applying a shift-reduce parser to a new problem, coming up with this oracle and what transitions you want to do. So if you have a new graph that you want to parse, you have a new type of tree that you want to parse, then coming up with, if you can come up with this oracle, you can apply kind of a transition-based method to it. So the main takeaway from this is that's not just for trees. You can also do it for graphs if you have a graph that you want to have.
So to like actually implement this with the actual parser, you would take the feed-forward neural network code and then add a few more actions, add the updates for the actions, and add a couple more features to do that.
Yep. So yeah, thanks. One interesting thing that that Dan said during our TA meeting, but he didn't say here, was if you look at the transitions of a transition-based parser, sometimes you can find transitions that are like swap, 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 reduce, swap, 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 or things like this. When you have a transition system that isn't like well adapted to the problem, though. So I did say it's as simple as coming up with your transition system, but coming up with a good transition system might not necessarily be a trivial task also. So I myself have not come up with a transition system, so I can't give advice about that, but it's worth thinking about, I guess. So the final thing I'm going to talk about this time is shallow semantics. And the idea behind shallow semantics, the most common version of it is semantic role labeling, but basically it's label who did what to whom on a span level basis. So the idea is she blames the government for failing to do enough to help. So blame is a semantic role. And when you blame somebody, there is a judge that's blaming somebody. That judge evaluates somebody, and there's a reason why they're basically blaming somebody. And each verb has different roles, basically. So blame has certain roles, eat has certain roles, decide has certain roles. So in a way, this is kind of like an open domain semantic parsing task, but it can be reduced to, it's open domain in the domain of basically verbs. So you'll have lots and lots of verbs that you don't really know what to do with. But on the other hand, you just need to label spans, which makes things a lot easier. And you need to, so the good thing about this is that you could then go and say, what do people tend to blame people for? Like, what are the reasons why people tend to get blamed, et cetera. So you can ask fairly deep questions about stuff. So neural models for semantic role labeling. There's a couple models for this. One of the interesting things is the model that currently works the best, I think, is basically just a deep LSTM model, where the input to the model is the predicate that you want to label. So it's all the words in the sentence, and then the predicate gets a binary variable 1 that basically says this is the semantic role that I'm looking to label, and then it just outputs tags that are beginning of argument 0, in argument 0 to the end of argument 0, then beginning of argument 1 all the way to the end of argument 1. So it's a super simple model. It doesn't even, I believe it doesn't even have a CRF or anything on top of it, but it works pretty well. And maybe the most interesting part of the paper is the analysis. The analysis shows a lot of things, like that this model is quite a bit better at everything than other models that have been proposed, but you can look at the details in the paper. So, yeah, that's all I have for this time. Are there any other questions about semantics related stuff? Semantic parsing related stuff? Okay, if not, I'll finish up here. Thanks a lot.